In this video, I'm going to be talking about the Diffie-Hellman key exchange. So the Diffie-Hellman key exchange, just like public key cryptography, is extremely important for communication over the internet. If you're watching this video, your computer has performed the Diffie-Hellman key exchange, either with YouTube or with servers or whatever, right? So Diffie-Hellman key exchange is a method of securely exchanging cryptographic keys over a public channel. So the Diffie-Hellman key exchange is a method of securely exchanging cryptographic keys over a public channel. That's what it is, right? So Diffie-Hellman key exchange establishes a shared secret between two parties that can be used for secret communication for exchanging data over a public network. The analogy illustrates the concept of public key exchange by using colors instead of very large numbers. And so it's talking about this. This is what is going on. We have a common number, or in this illustration, a common paint. Then we have two secret colors, Alice and Bob. Okay, Alice and Bob want to speak to each other. Alice has the private, Bob has the private. These two, this is the public, right? This is the public number, the public color that we're going to be communicating with. Alice adds her color, which results in orange. Bob adds his color, which results in going from turquoise to light blue, or they exchange it, right? So now if an adversary is watching, he sees this and he sees this, but he's not seeing the two colors, right? He sees this, he sees this, he sees this and this, right? So we exchange these two colors, but he doesn't see the red and he doesn't see the blue because these are the secret colors, right? So So now they've exchanged these two public colors that are mixed with their secret color, and it's very difficult. It's very difficult to separate these colors. Very difficult, right? So it's very difficult to take this and separate the red from the yellow. It's very difficult to take this and separate the blue from the yellow. Okay. Now, what Alice is going to do is she's going to add her secret thing to this blue thing and end up with a common thing, right? And then we end up with this. And then Bob's going to do the same, right? He's going to add his thing to Alice's public thing, and then he ends up with this, right? So this is the shared thing, right? This is the shared number, the shared color, the shared secret, whatever it is, right? And this shared secret is how people exchange, right, keys for AES, so they can communicate securely over a network. So AES being advanced encryption standard for symmetrical key cryptography. Anyway, so that's what Diffie-Hellman. It's really hard to explain, but I'll just try and read this. The process begins by having two parties, Alice and Bob, publicly agree on an arbitrary starting color that does not need to be kept secret, but should be different every time. In this example, the color is yellow. Each person also selects a secret color that they keep to themselves. In this case, red and blue-green. The crucial part of this process is that Alice and Bob mix their own secret color together with their mutually shared color, resulting in orange tan and light blue mixtures, respectively. Then they publicly exchange the two mixed colors, and finally each of them mixes the colors they receive from their partner with their own private color. The result is a final color mixture, yellow-brown in this case, that is identical to the partner's final color mixture. If a third party listened to this exchange, it would only know the common color yellow, and the first mixed colors, orange, tan, and light blue, but it would be difficult for this party to determine the final secret color, yellow-brown. Bringing this analogy back to real life exchange using large numbers rather than color, this determination is computationally expensive. It is impossible to compute in a practical amount of time, even for modern supercomputers, right? So basically what they're saying is that if you were to turn this all into math, it's extremely hard and extremely expensive, even for modern-day supercomputers, to turn orange back into red and yellow, or to turn blue back into turquoise and yellow. That's what it's saying. Is that, yes, it can break the math code, but it's extremely, extremely time-consuming and difficult and long. So That's what the Diffie-Hellman key exchange is. It is simply a method that your computer uses for exchanging cryptographic keys over a public channel, over a channel that's being monitored publicly.